Вопросы можно задавать по-русски, если что-то, но читать будем по-английски. Okay. So during this seminar, we will present our work, our result about decidability if two given Legendrian knots are equivalent or not equivalent. Yet unpublished result. So our ultimate goal is to introduce some diagrams we have so-called rectangular diagrams, and now I simply call them by diagrams. Moves of diagrams of links and complexity. So we have some diagrams, some moves, and complexity. And moves of diagrams preserve topological type of link, and any link can be presented by some diagram. And we want suppose we have some diagram of link, then we try to simplify it by some moves. So this axis is complexity. We try to simplify it by some sequence of moves, and at some moment we arrive at non-simplifiable diagram, the diagram that cannot be simplified. So our hope is to classify all such non-simplifiable diagrams. So goal. And on each for every simplifiable diagram, we want to have some algorithm to find a sequence of moves, of simplification moves. And in the end, we want to have some good algorithm to distinguish topological types of links. Okay, so I would like to mention some people. The main inspiration in the beginning of the whole work was the works of Haken about decidability if the given knot is trivial. we use techniques which were introduced by Лекция in some simple form. So we extend his techniques. And also his techniques were already extended by Joan Bierman, Bill Menesco, and Peter Cromwell. The second point, it occurred that rectangular diagrams are in very close connection with contact topology. And we use many ideas introduced by Giroux, Honda, and Etnaya. Okay, so I begin with definition of rectangular diagram. I'm sorry if you already know it.
Первый вопрос хочу задать. Это первая лекция или вторая? Первая.
So, we have a torus with theta and phi coordinates on it, and rectangular diagram is a finite set of points on the torus, such that on each horizontal and vertical line there are exactly 2 or 0 points of the diagram. Okay, for example. So we can draw a diagram on a square which is glued up to the torus. These points are called vertices of the diagram, and the lines, vertical and horizontal lines, which contain the vertices, at least one vertex, are called levels. So this is vertex and this level. We can associate with every rectangular diagram a planar diagram of a link. In the
Level only horizontal or vertical is also level?
Horizontal and vertical also. Okay, so draw segments on vertical levels first, then draw horizontal segments such that the vertical line is always overcrossing. This is very simple diagram. So denote by this the complexity of diagram, which equals to number of vertices. Another way to see a link is join representation of the diagram. So recall that three-dimensional sphere is the join of two circles. Denote by theta the coordinate on the first circle. Suppose it belongs to the segment from 0 to 2 pi. And phi, the coordinate on the second circle. Denote by tau the join coordinate. So let's draw a picture. This is the first circle with theta coordinate. This is the second. And every point of 3 sphere lies on some segment connecting these two circles. Note that the direction of increasing of tau coordinate is from the second circle to the first one. It's maybe uncommon for joint construction, but we do so because we want that the basis tau phi theta phi tau is positive oriented basis. So maybe I can draw some vectors here. This is so one can see that this is true on this picture. Okay, so our torus is the level set of tau coordinate is where tau equals 1/2. Tau belongs to segment from 0 to 1. So, suppose we have some rectangular diagram on this torus. For every vertex of rectangular diagram with coordinates theta phi, we associate a segment in the join which connects points on circles with theta coordinate and phi coordinate respectively. Okay. So it's hard to draw the join picture for this diagram, for example, but the idea is simple. For every segment, for every edge, these segments are called edges of rectangular diagrams. Every edge corresponds of rectangular diagram corresponds to a vertex on the one of the two circles of the join. Vertical edges corresponds to so vertical edge, for example, theta equals theta 0 corresponds to the point on the first circle, and horizontal edges corresponds to points on the second circle. Okay, so we have two realizations of rectangular diagram. We have two ways to represent link. These ways are equivalent, and we will see this in next maybe hour or so. So we consider oriented rectangular diagrams. Orientation. Orientation is a checkerboard coloring of the vertices of the rectangular diagram. For example, something like this. Each component of a rectangular diagram can be oriented in two ways. We consider the following rule. On each vertical level, the segment directs from painted vertex to unpainted one. So in this picture, and on each horizontal level, the segment is directed from unpainted vertex to painted one. So let's draw it. And in the joint picture, if the vertex is unpainted, then the corresponding segment is directed from the first circle to the second, and vice versa for painted circle, painted vertex. So this is orientation.
I guess in the paper version, painted is black and unpainted are white, or?
Yes, yes. Also, we need framing of rectangular diagrams. So, on each level, we have a choice between two segments on the torus which connect two vertices. So this is picture on the torus. So make this choice for all levels, for each horizontal and vertical ones, and this choice is the framing of rectangular diagram. So the number of framings of the given rectangular diagram equals 2 to power of the complexity, the number of vertices of rectangular diagram. So this is the number of framings. Okay. So suppose we have some framing F. And consider its joint realization. F hat of framing F. So, the joint realization of framing is a ribbon which consists of pieces of two types. So we glue the ribbon from two types of pieces. First one, suppose this some piece of rectangle diagram here. So this is join realization of rectangular diagram, the part of it. So the first type of piece is a sector. Sector with sides along edges of link. So in each vertex we have two sectors with the same sides. This and the opposite one. Okay, so the choice between two sectors corresponds to the choice between these segments, which was done. This choice was done when we determine the framing. So so is it clear that one of these segments corresponds to some portion of tau coordinate, which corresponds to some segment here, and the other segment okay, I can.
To me it is clear, but I'm not sure that it will be clear to anybody.
Okay. Okay, so there is natural correspondence between segments and sectors. So when we have a framing, so we have only one sector in each vertex of link. So, for example, let's draw in this way. This is the first type of pieces. The second type is a small ribbon along each segment connecting two circles, our joint circles. And this ribbon have to rotate in the minimal way. So in this picture, we drop the ribbon in this way. So the portion of our ribbon f hat will be here like this. Okay, one more example, the same example. I switch one sector, for example, like this. So in this case, the minimal rotation means that we rotate in the positive direction here. So here we rotate in positive direction. And here we rotate in the negative.
And why the choice of minimal rotation is always unique? Normally it is some circular coordinates, and if you have opposite points, it is not unique. Why? this cannot happen here?
Opposite. In which case is unclear. Which case?
I pose the question. Why it is always unique? I cannot imagine all possible cases.
Okay. So different choices differ by rotation by some number of 2 pi's. Yes?
Yes, it is. You must relate 2 angles.
Yeah.
But if these angles are opposite, you can go. If you must relate by the minimal arc 2 opposite points, you may go one way or another way. Both are minimal.
If these vertices are opposite?
If the angles are opposite. First of all, I don't understand what angles are supposed here. Maybe geodesic. Yes, okay.
Yeah, you can imagine this. You have Riemann metric on the sphere, standard Riemann metric, and these segments are geodesics. You can suppose this, and you have parallel transport from this point to this point along this geodesic, and I don't remember.
You never arrive to the opposite vector.
1 minute.
Yes, of course, because they are orthogonal to each other. It's okay. So they are not opposite.
Okay.
Okay, so it's okay. The framing vectors, normal vectors to the segment.
Yeah.
If you translate, you obtain orthogonal vector.
Orthogonal vector, yes.
Okay, so it means that there is always the unique way of rotation.
Yes. There is
The ambiguity may appear only if they are opposite, if the angle is pi, but here it is always pi over 2.
pi over 2, yes.
Okay, so no problem.
Okay. Now I realized your question, yes. So yeah, there is some unique way to rotate in the minimal way. In the following way, we construct the joint realization of framing. It is some ribbon in the three sphere. Denote. So this ribbon have 2 boundaries, 2 boundary components. One of them is our initial link, and the other is the other component we call by smoothing. Smoothing of the link with respect to the framing F. So, we have this ribbon F hat. It has 2 boundary components. One of them is our link, and the second one is what we want. So we have a smoothing of our piecewise smooth link. We had a piecewise smooth link, and now we can obtain a smooth link. So now we are ready to prove that two ways to represent rectangular diagram as the link, the planar diagram and the joint realization are equivalent. So now we construct an isotopy between joint realization of the rectangular diagram and its associated plane diagram. So, consider some diagram. So this is associated plane diagram, and we have some standard framing of rectangular diagram. So we choose these segments. Call it standard framing of rectangular diagram. So the framing on the picture.
It depends on choice of source of infinite lines.
Yes, it depends. So we have some
choice of presentation of torus.
Yes, we have some line theta equals 0, phi equals 0. So
you fixed coordinates.
Yes, coordinates are fixed. Yes. If we consider some combinatorial class of rectangular diagrams, then we have no standard framing. But now we have. Yes, and consider the smoothing of link R hat with respect to the standard framing. This link does not intersect circles of the join, two circles of join, and so we have a projection of this link to the torus along tau segments. And I claim that this projection looks like this. So it looks like simply like smoothing of this diagram. So okay, how it looks. So the portion of ribbon which goes along the boundary of the sector projects to the line which is near the corresponding segment. So the boundary of the segment projects to this segment. So the smoothing goes like this. So okay. Yes. Some portion of smoothing coincides with the segment. This is the part of projection. And this portion of smoothing is near the vertex, projects to somehow near the vertex of rectangular diagram. So it looks like this, for example. So the projection of smoothing looks like the smoothing of the corresponding plane diagram associated with rectangular diagram. So it is. So that's all.
Maybe it was to remark that if you compress all these pictures to a small piece of your torus, then this projection along the joint coordinate is a good approximation of standard linear projection,
Yes.
which is used to represent block diagrams.
Yes, a good observation. Yes. So we can always assume that our whole rectangular diagram lives in a small piece of torus, in small rectangle, and so the whole picture is like in the standard R3. So there is no problem. Okay, so now we have two ways to represent rectangular diagram and their equivalent. Okay, so let us mention that every link can be realized by a rectangular diagram. So to do that, first of all, we can consider just some plane diagram. For example, like this. So we can assume that our whole link lives in the small neighborhood of our torus, which is tau equals 1/2, and is very small. Yes, so consider some its plane diagram, then then rotate each crossing such that the overcrossing becomes vertical and overcrossing becomes horizontal. So I'm sorry for this picture, but so first of all, okay, then approximate the diagram by rectangular lines, something like this. So the number of edges doesn't matter. We can have any good approximation as we want. So, like this. So in the end we have the same, combinatorially the same plane diagram of our initial link, but now it is associated with some rectangular diagram, and so that's all. So we have a rectangular diagram of every given link.
Wait. The picture of a link that you draw in the beginning is different from this, but
oh, I made a mistake somewhere. Yes.
Yeah, but it's okay. Everybody, I think, understand how to change it.
So where is the mistake?
The first diagram wasn't alternating.
Yeah, it wasn't. I tried to draw alternating diagram, but okay.
The mistake was in the previous. This picture is perfect.
I'm sorry. Yeah. Okay, so now with every rectangular diagram, 4 braids are associated. With every oriented rectangular diagram. Yes. So, consider some diagram, some example. Then choose one of the 4 directions. For example, we choose the right direction. Then take every horizontal segment which is directed to the left and inverse it. So you obtain some framing. Yeah, all of the remaining horizontal segments are directed to the right. Then you can slightly smooth this picture to obtain a true braid. So, like this. So we want that any strand always goes to the right, and so we need to have some slope here. I don't know. Okay, denote this braid by this. We will speak about connection with braids a bit later. And now I want to introduce some numbers associated with every rectangular diagram. First, there are 8 numbers. And the first 4 numbers are called classical invariants. Of rectangular diagram. So, the first one is Thurston-Bennington number which equals to rise of rectangular diagram. It's associated plane diagram more precisely, minus a number of its angles it's down these angles I call it right down angle. So
our rectangle diagrams are oriented or not?
Yes, but in this definition it doesn't matter.
We use framing here, no?
Yes, because
Yes.
height also depends on the frame.
Yes, we consider standard framing. So
Standard.
Standard.
Any framing.
standard.
This is only for the standard.
Yes, standard. Okay, let's draw some picture for which we will compute all the invariants. So,
And what means this TB and lower index?
Thurston-Bennigan number, the first.
This is
There will be two Thurston-Bennigan numbers. This is the first one. So it will be the second. Okay, an example. So, so we can draw here. So the right, yes, orient diagram in any way. The right is the number of positive crossings minus the number of negative ones. So in this picture, I suppose all crossings are positive.
But the diagram should be oriented, otherwise you cannot.
Yes.
It depends on the relative choice of orientation of components.
Yes. If it is, if it has several components, then we must have orientation. Yes. So yes. Okay. Yeah. Oriented rectangular diagram. Okay. So in this picture, all crossings are positive. So right equals 3. And we count number of such right down angles. This one, that's all. Two angles. So in this example, we have first Thurston-Bennigan number equals to 1. The second Thurston-Bennigan number can be defined in terms of reflection with respect to vertical line. So denote by small r the first, the reflection, sorry, not the first, but in the sub-index we have just a vertical line. So this is reflection with respect to vertical line. Okay, vertical line. And we can define the second Thurston-Bennigan number like this. And we have a formula also.
What is the reflection?
The whole diagram, the whole rectangular diagram is reflected with respect to horizontal line. So in this case, we have a minus, right, and minus number of corresponding angles, also reflected. You can note that number of angles of such type equals to the number of angles of such type. So in this picture we have two of them, here and here. It's clear from the following observation. Project the whole diagram to the line. In this case, theta equals minus phi, this line. And you see that the projection have разворот.
U-turn. U-turn.
U-turn?
Ну, как буква U.
Yeah, U-turn, yes. Okay. So the projection has U-turns in some points. And you must have the same number of U-turns of from the left to left and from the left to right. So it's clear. So you can change in this formula this number of angles by these angles or by their sum divided by 2. So okay, so these are first two classical invariants, and the second two are rotation numbers.
And what is the result of this example?
Yes, we didn't compute the second Thurston-Bennington. So for the second Thurston-Bennington in this example, the RIF is 3, so minus 3 minus number of, so 1, 2, 3, yes, minus 3. So it is minus 6. It is clear that the sum of two Thurston-Bennington numbers equals to minus complexity of the diagram divided by 2. So it is clear because in the sum the right cancels and we have only number of angles, and it is clear that it's this number. Okay. So there is some geometric meaning of this number. So let F be a framing. Denote by F in triangular. Okay, so denote by this the linking number. with its smoothing with respect to. So it's just the Lincoln number of components of joint realization of framing of the ribbon. And the proposition is that this number belongs to segment, so it cannot be very large or very small. The minimum is the first Bennigan number, and the maximum of this number is minus the second first Bennigan. Okay. Why this is true? So it is easy to locate the case when the Lincoln number is maximal or minimum. So our ribbon rotates rotates by pi over 2 angle of pi over 2 along each edge of our link. And sometimes it rotates in the positive direction, our ribbon. So okay, just for example, here, yeah. In this case, it rotates in the positive direction. Sometimes it rotates in positive direction, sometimes in the negative. And the maximum of this Lincoln number is when we rotates always in the positive direction, or always in the minimum. So in the terms of rectangular diagram, the maximum means the fact that we rotate always in the positive direction means that in the diagram we have such picture. We always go to the right and down, right, down, or always up, left, up, left, up, left. So all angles of the framing are of these two types.
Чтобы был максимальный или чтобы был минимальный?
Maximal. So okay. So maximum, we achieve the maximum at when all angles of the framing are of these two types, this and this. And minimum in the opposite situation.
I'm sorry, it is obvious?
Yes, it is. Yes. So consider an example. Yes. For example, in this picture. Yes. So let's draw this vertex. Okay. The vertex corresponding to this edge. Okay. So this. It's horizontal. So and oriented somehow. its horizontal end directs to the left. Yes, because we have this sector here. Yes, so theta decreases along sector. So this is the horizontal and a piece of horizontal edge here. And what we have about, yes? Okay, I just finished the picture. So here we have phi increasing. Phi increases, so here this is positive rotation, so we have this angle. Okay. And what about this formula? Okay, we know how to compute this linking number in this case in combinatorial terms. The smoothing we can consider not the smoothing of the link, but we can move the link in the transverse direction to the ribbon. So here the ribbon is oriented because our link is oriented, and with respect to this ribbon we move our link in the positive direction. So here we have, so this vertex move here, phi increases, and here theta decreases. So what I claim that this linking number can be computed as the linking number between our initial link and its modification like this. So every vertex, what I denote by this. So, choose some epsilon, and for a given rectangular diagram, move any its vertex to the by the vector minus epsilon epsilon. And the obtained rectangular diagram we denote by this with this arrow. So I claim that I claim this. So compute not the linking number between boundaries of the ribbon, but move the link in the perpendicular direction to the ribbon, and this is equivalent to this. In any place theta decreases and phi increases.
I have a little question. In the last notation, you do not use framing.
Yes, but I suppose now that we have maximum framing. So I prove this statement, and I consider the case when f has maximal linking number. In this case, so we have positive rotation along each segment, and so on, so on. So yes, thank you. I should write here something that if the linking number is maximal. Okay. And this number can be clearly computed in purely combinatorial terms. So, draw some crossing of a rectangular diagram R. After moving, we have picture like this. Yes. The white one is R, and the I guess orange is moved one. And here it is clear that all such crossings give rise of R to this linking number. So this linking number is a sum, or some sum of over all crossings. So here, suppose, every crossing of R contributes its sign to this sum.
Twice.
Not twice, once. When we compute, when we
Yes,
okay.
yes, it contributes twice. Two crossings, which means one to the linking number. Okay.
Yes, one to the linking number. Okay. So, yes. Also, if we have, for example, such corner of the rectangular diagram R, so we have this picture here. So this corner doesn't contribute to the sum. Here we have a contribution. It is positive. Yes. Here we assume that there is no contribution because we just count all crossings between these two diagrams in which over crossing is moved diagram. Okay, so we count only those crossings where over crossing is move diagram and under crossing is the initial. So this doesn't count. And the final case is this. So there is no contribution here. So we have y plus 1. I'm sorry. Y plus 1. Plus 1, yes. It's okay. It's okay. It's okay. But no. Let's draw some orientation here. But no, there is no. Yeah. So we have plus number. This it's okay. So plus number of corners of such type. And this is the formula that we had initially.
Will you explain why you should? So you take the standard framing, no? Standard diagram.
Yes.
But which so not the diagram corresponding to the framing. It means that you always choose. You do not have the choice of horizontal segments. You always.
Yes, I always choose the shortest. Yes.
Which doesn't cross
the boundary of the square.
Yes, the boundary of the square. And why should you move?
So what?
How do you comment this equality?
This equality.
Yes.
So so suppose f is maximal. So we suppose this.
And sorry, one more question. Where is involved this observation? So it is has not this observation that you always turn.
Okay, so
turn like this has nothing to do with the proof of this formula.
Okay, once more, I repeat. So suppose this number is maximal. In this case, we must have this.
Okay.
We don't use it explicitly, this fact, but what does matter that in the maximal case we compute the linking number. We compute the link number not between these two guys, but with this guy and this guy moved in the perpendicular direction.
Yes.
And when f is maximal and we have this situation and so on, the moved guy is obtained. This is this one. Why? So I just draw this picture. I considered one case. I should consider all cases. So in this picture, if we move in the perpendicular direction, so this point moves, phi increases, theta decreases, and I claim this is this will be everywhere, and so I write this arrow everywhere.
So you must choose all the possibilities.
Yes, we should consider all cases. There are four of them. Similarly, the proof is the same for the minimal framing, and so it's so the linking number is bounded above and from the bottom, and this is the geometric meaning of this Thurston-Benneken number. Maybe we should have a break, some short break.
May I ask a little question?
Yes.
Are these boundaries sharp?
Yes, of course. So you can choose the framing when you always, yes. There is no problem.
Just computed this number for the maximum for minimum framing.
Yeah, so this is maximal framing.
Ладно, то есть короче, перерыв делать, да? А долго ты еще собираешься сегодня рассказывать?
Ну,
Сейчас точно который час?
сейчас 7:39. Okay, so we defined two Thurston-Benneken numbers. Two more invariants. So, first rotation number is the following number. So we just compute some angles and some convex, and we care about orientation. And the second can be defined in a similar way, but for shortness we write this like this. Reflect the rectangular diagram with respect to vertical axis and compute the first rotation number. So these are rotation numbers. So their meaning maybe now is unclear maybe, but just define. We define 4 numbers and we want 4 more. They're called self-linking numbers.
Self-linking number is not a classical invariant.
Yes, yes. Of oriented rectangular diagram. So, consider the braid. For example, this braid. And there is a well-known invariant of the braid. Self-linking number of some braid equals to minus number of its strands plus the algebraic crossing number. And this is actually any braid has two self-linking numbers. Here is the first one, and the second one is so the first self-linking number is invariant if we apply positive stabilization to the braid, and the second self-linking number is invariant if we apply negative stabilization to the braid, Markov stabilization. Okay, and we can compute. Let's give some example. Just any example. For example, here we have n equals 3 strands, and algebraic crossing number is 0. So both self-linking numbers equals to minus 3. Okay, so self-linking number of rectangular diagram is one of the four numbers. So you can ask about, oh, sorry, I had this notation, I forgot. The error is in the upper index. You may ask, what about braids which are obtained from rectangular diagram by considering framing where we inverse all only vertical edges, yes. We invert only vertical edges. So there you obtain the same numbers. So there it's not interesting.
What is the correspondence?
So between what?
Between these and the other four numbers.
The correspondence. Okay, I don't remember. And the theorem is that, for example, this number equals first Thurston-Benneken minus first rotation number. And this is So let's compute the self-linking. So, okay. Suppose we have some rectangular diagram. It has some right, yes, and algebraic crossing number of the braid so we will consider this braid is somehow related to the right of the rectangular diagram. So some crossings survive after inversion of some horizontal segments. So what happens when we inverse the segment? Okay, so we have some edges here and some edges here and here. So they are oriented somehow, and consider 4 cases. One of them depending on which direction is have these 2 guys, vertical edges, up or down. So I claim that in this case the algebraic crossing number, the algebraic sum of these crossings is sorry. So in this case, how to say? So
it doesn't change because the sum of all is 0, and when you go there, you change the orientation.
Yes, essentially you are right. Yes. So the number of times when we move down equals to the number of times when we move up along the edges. In this case, because we cross some line, so these numbers are equal, and each segment which directs down in here
contributes one sign, and when you
yes,
switch, it contributes the opposite sign.
The opposite sign, yes. So in this case, if we inverse the segment, the contribution of these guys is equals to those guys. So it doesn't change. So consider some other cases. So this case is similar. So interesting cases. This is interesting case. So here along this segment we move from bottom to top. So here we move down one more time, then we move up. And this give let's draw a picture. So here we move up. So for example, 3 down, 1 up. Here 3 up, 1 down, and 1 down. So no.
Erase one more.
I must erase something.
Yes. The leftmost, for example.
The left, yeah, okay, thank you. Oh. So in this case, these are all -1, -1 plus 1. After inversion of the segment, this is -1, -1 plus 1, -1 plus 1.
So, except that for me, this is +1. Change the sign to be conventional.
Everywhere.
No, everywhere, yes.
Okay.
No, it's okay. No, it's okay.
Oh,
It's okay.
it's okay. The vertical
Yes,
is
yes.
overcrossing. So here we have -2, and after inversion we have -1. So this inversion contributes +1. And similar case is this. I claim that this case contributes -1, each such case. So okay, so let's now then no more pictures, just formulas. So right is Thurston-Benniken plus 1/2 of number of these corners plus number of these corners. Okay. Sorry, I maybe forgot something. Yeah. So I should write this. Yes, I continue with this expression. So -n is just the number of edges which directs to the left. So
Why?
by definition of our braid, so we inverse only such horizontal edges which directs to the left. So, and our braid always goes to the right.
Okay.
And the vertical edges are not altered. Okay, this is minus n. Then the other stuff. And so on. So we can write this guy more specifically, considering all such cases. This sum is this guy, and this. So yes. So okay, this plus this. You can see that this guy cancels. So
not this maybe, but
Yes, this. Not the next.
nearby. Right.
oh, sorry. Yes. Sorry. Yes. And we have. So I made a mistake. And we have two such guys. Yes. So I erase this guy and put 2 here. Okay, then so I will just erase this. Then write this more, consider more cases here. Note that this guy is the sum of this and this. Yes? And this guy is equal to the sum of this and this. Sorry. Yes. Thank you. So we see that if we sum up, so all this guy cancels, and what is left is this.
Why they cancel? Because here we have
No.
half.
Oh, sorry. No, they don't cancel, but some. So I write it. Okay, plus 1/2. Then minus this. Minus this. And plus this. And this is precisely the definition of rotation number. So, okay, so this is just some computation in combinatorial way. This formula can be obtained very similar. So for this, let's do it now. So note that we can reflect the diagram with respect to vertical axis. So consider R vertical of R reflection. Consider the braid where we inverse every edge which directs to the right, to the left, not in this case. And note this equality. So when we reflect the diagram, all signs of crossings changes. So number of strands is the same, but the algebraic crossing number changes its sign. So here plus and minus, and that's why here is 2 and here is 1. But for this guy we already have formula, this. So we apply it. Then note how these classical invariants behave under the reflection. By definition, this is just the first maybe. By definition, we have this. Yes, just R, and the same here, but yeah. So we have plus here. And we can guess that the last formula is, so here we have plus, so here we have minus. So there are four numbers. We can think of these four numbers, or of these four numbers, and they're related. What's
Can you explain why these numbers are interesting?
yes, yes.
Just a linear combination.
I'm going to say this now. So there are some moves of rectangular diagrams.
I have one more question. Why we call it rotation number? What is the explanation of this terminology?
The terminology
What rotates?
it is the terminology from contact topology.
Okay. It's rotation number
Of tangent vector of Legendrian link. So there are some moves. First set of moves is stabilizations and reverse operations are destabilizations. So suppose we have some vertex of rectangular diagram and substitute it with three other vertices, which with this deleted one form as a little square. So this vertex is deleted and we add three more vertices near it. We can do this in four ways. Consider some example. So let's draw some edges here. So this is stabilization, and there are some types of stabilization. Suppose our rectangular diagram is oriented, and without orientation. These two stabilizations are of type 2, and these type 1, and these two stabilizations are of type 2. And if our rectangular diagram is oriented, we call some stabilization of type, for example, 1 and the arrow to the right, if the small h, which is added, directs to the right. So this arrow coincides with this small horizontal arrow. This is the rule. So we have four types of oriented rectangular diagram. For example, if we have such orientation here, then this stabilization is of type 1 left, This is one right. Oh, sorry, two, yes, two. Here one left, and here one right. And look how our numbers change. So Thurston-Benneken and rotation number of type 1 do not change, are preserved. By type 1 moves, by type 1 stabilizations and destabilizations. And the same is for the second type. If we apply stabilization of type 2, okay, so in this picture, how Thurston-Benneken changes. So it's some rise, yes, minus number of corners. So we have such corner here, and the rise is, the contribution to the rise is -1. So here we have contribution minus 2, sorry. No. What is contribution of this move to the Thurston-Benneken number? -2? Yes, no?
So maybe we should write a formula for the first term.
So yes, Thurston-Benneken. Right minus some no, the number of such corners doesn't alter, so we had one and we have one, so yes. So here contribution is -1. Type 2 stabilization contributes to first Thurston-Benneken -1. And what about rotation number? So so here something. So have some formula for rotation number on the board, blackboard not. No. This with plus or with minus?
Yes, with plus.
With plus, yes. Okay. And this?
With minus, if I'm not mistaken.
With minus. It's suspicious in some sense. So the rotation number, if we rotate the whole diagram by the 180 degrees, then rotation number doesn't change. So I guess that we must have some symmetry here. So if we rotate this by, so we should have here and here the equal signs. But where? Okay, so I suppose we have minus here.
In the previous formula it was plus.
Oh, that's bad news. So, okay. So I think this is correct. Okay, so I think I have formula somewhere. Oh yes. So
now we're trying to understand how the rotation number changed with
changed.
when we proceed the moves.
Yes, when we apply the moves, how our numbers change. Here I have the same mistake. So I should think of it. So what is the right formula for rotation number? So I thought that it should be invariant under rotation by 180 degrees, but it isn't. And what formula we obtained in the proof of the formula for self-linking number for this formula. Is there some?
I didn't copy.
Okay. So we have no right formula, but so I think.
Maybe now we are not going to find a mistake, and
Okay.
you will say us
Yeah.
the right formula on the next seminar.
Yes. So I think something like this should be right. Okay. So here we have it is here with minus, yes, and this is with plus. So rotation number increases by 1. This here it decreases by 1. Then now consider how self-linking number changes.
Which number?
Self-linking numbers. So I will erase something. I think this.
Может, ты перепроверишь эти все вычисления, потом пока не вижу.
I think this is okay. I will.
Вдруг там тоже что-нибудь так будет.
Okay. So.
Можешь вообще, может быть, скажешь, к чему это ты клонишь вообще?
So self-linking number is invariant under all types of stabilizations except one. So here we have the formula, and when Thurston-Bennington decreases by 1 and this increases by 1, then we have some change. So if we apply type left stabilization, then this decreases by 2. And in all other cases it preserves. So the same is true for other four self-linking numbers, and so we have some four numbers defined for rectangular diagram, which remember how many stabilizations of each type we already applied.
You mean stabilization minus destabilization?
Yes, yes. There are other moves called exchange moves, and they preserve all numbers. So exchange moves do the following. Suppose we have two adjacent levels of the rectangular diagram, and four vertices on these levels goes in the non-interleaving manner. So
Non what?
non-interleaving.
How do you write what?
So these two segments interleave. And these two do not interleave. So this is forbidden situation, and we consider just this situation. And in this case,
I heard the word non-crossing partition.
no crossed partition. Oh, that's interesting. So in this case, we can just exchange these levels. So we vertices are moving, keeping their
All the rest.
keeping the rest coordinates. And of course you can move levels such that you can along the torus, not changing the order of these levels, and the underlying link is preserved by such transformations. So the theorem is
And all these numbers are also preserved?
yes, by these moves, yes.
Oh, if you, how to say, do cycle permutation.
If we
If you change
do
the origin, if you change the zero meridian,
yes,
all these numbers are preserved?
all these numbers are preserved if we change.
Evident. Okay, I believe you.
Yes, they are all
But
preserved.
did you check it?
Yes.
So can you repeat the question, please?
If we so
If we change the framing or what?
if we move levels along the torus, so
If you change the coordinate on the torus, the origin,
Okay.
the zero angle, the zero
Okay.
so some h jumps to the other side. Yes, if we move it. So we had some corners here, but now the corners are changing, so it's not immediately clear that all numbers are preserving, but
not only corners changes, everything changes.
yes, crossings, the number of crossings, all changes, but yes.
The number of left, no, this doesn't change. The number of left oriented and the right oriented is the same, yes.
So yeah, for rotation number, it is evident that. So
Okay.
so it's not hard to see that rotation numbers and Thurston-Bennington are preserved by this. Okay, and the theorem is that this set of move is sufficient to connect any two rectangular diagrams of the same topological link type.
Перекидывают, вроде бы наоборот, знак будет поменять. Сейчас. Ну да, то есть эту ты убавил, эту прибавил. Нет,
This corner also changes. So in this picture, 4 corners are changing. So yes, we should consider some cases. Maybe there are some maybe 16 or some power of 2 cases. So, and I finish by claiming the theorem. I think it's proved in some other terms, first by Cromwell, and then for rectangular diagrams. Cromwell proves the theorem for combinatorially equivalent objects to the rectangular diagram. He proved the theorem about some arc presentations, but they are equivalent combinatorially. So, so two diagrams represent the same topological link type. If and only if they are related, by stabilizations, destabilizations, and exchange moves. And also we are considering all on the torus, so we can move along the torus. We consider only combinatorial class of these diagrams. So I think that's all for today.
Are you going to prove this theorem or not in the next semester?
I don't know,
Okay.
but it's we can, if you want, we can.